इसमें सर आपकी आवाज नहीं आ रही।
Okay. Unfortunately, the mic was muted and I didn't know. Okay. I will start it once again. This is the design of reinforced concrete beam for shear, lecture number 6. The topics included in today's lecture are shear stresses in rectangular beams, diagonal tension, NRC beams, types of cracks, shear strength of concrete. These topics will be discussed. The students will be able to understand the design of shear, the design of reinforced concrete beam for shear as per ACI code provision. So, okay, we were discussing this thing. At the shear stress variation at a point in any section in a homogeneous elastic rectangular beam, which means that the beam is made of a material which is homogeneous, not composite, and the stresses are within the linear elastic range. So this can be true for a pure concrete beam, for a plain concrete beam, when subjected to very small loads, so that stresses are within the elastic range, or for a steel beam, even at much higher load, because steel beam exhibits elastic response up to the yield point, so much higher load can be resisted by steel beam within the elastic range as compared to a concrete beam, because concrete beam cracks in the very beginning, at a very early stage as compared to its final stage. So the linear elastic stage in a concrete beam in a very early stage is possible, otherwise it is not possible. Okay, so if the stresses are within the linear elastic range and the beam is made of homogeneous material, then the stress variation through the depth of the beam, okay, this is, let's say this is a beam, so, and this is supported like this. If you take a section of this is a rectangular beam like shown here. The stress variation through the depth of the beam, through the depth of the beam, like in this range, depth of the beam. Take a section of this, so this is the depth of the beam. Through depth variation, this is called through depth variation, because you would have seen while you were drawing shear force diagram for a beam, that shear forces vary along the length of the beam. This V is shear force, this varies along the length of the beam. But when we talk about the shear stress through the depth of the beam, then it can be expressed by this equation. This equation is more or less similar to the equation used for flexure stresses. The variation of flexure stresses through the depth of the beam can be represented by this equation. This we have discussed quite a few times. If you compare this equation, all the parameters, if you compare the parameters of equation in shear with the parameters of equation in flexure, you will see that V can be compared with M, because this is a shear stress variation, so there is shear force which is taken from the shear force diagram, and in the flexure stress there is a bending moment M which is taken from the bending moment diagram. Okay, and then we have Y, which is the depth of the section which is at which the flexure stresses are to be calculated from the neutral axis. So this is the depth from the neutral axis. For example, if you want to calculate shear stress at this location, flexure stress at this location DC, so this will be Y. This will be Y for flexure stress. But Q is a little bit different. Q we will discuss next. And then I is moment of inertia. I is same in both the equations. And there is another term B, which is again the width of the section, width of the rectangular section. So I and B, the product of IB The product IB is also a geometric property. This is geometric. So this is geometric property. I and B both are geometric properties. So I and B will remain constant along the length of a beam if the beam depth and width does not change along the length. V is shear force and Q is a statical moment, which we will discuss next. Okay, just to understand this VQ divided by IB, we will very quickly discuss the case of flexure stresses so that you can recall what we have already studied. In the case of flexure stress, F is equal to My by I, you know that for a simply supported beam, the bending moment varies along the length of the beam. This is a case of uniformly distributed load and simply supported beam. The bending moment, the shear force diagram will vary such that there will be maximum shear stress at the support, and then it will become zero, and again increasing to the other support, and you have a bending moment diagram which is maximum where the shear stresses are zero, and then, so if you look at the two diagrams are quite opposite to each other. Where the shear force is zero, bending moment is maximum, and where the shear force is maximum, the bending moment is zero. Okay? So let's talk about the flexure stress first. If you want to calculate flexure stress anywhere along the length of the beam, so the bending moment will be picked up from this bending moment diagram. Let's say you want to calculate flexure stress at this location. So the M value will be obtained from the bending moment diagram, which you can obtain very easily. And the Y, okay, so this variation of the flexure stress equation, if you look at this equation, so the variation will depend on the bending moment diagram. The maximum bending moment occurs at the midspan. So the maximum bending moment can be obtained at the midspan, but if Y is taken as zero, so you would have zero flexure stresses. This is the neutral axis. And you know that the stress diagram varies like this to the depth of the beam, stress diagram in the linear elastic range. So we have zero stresses. When Y is zero, flexure stress will be zero, even if M is maximum. But if M is maximum and Y is also maximum, this can happen at the center of the beam in this particular case. In the extreme fibers, when Y is H by 2, either in the compression or in the tension zone. So when Y is H by 2 and M is maximum, because I is constant, so I will be constant if width and depth of the beam does not change along the length of the beam. Let's say the depth and width of the beam does not change, they do not change along the length of the beam, so I will be constant. When I is constant, then F is equal to My will depend on M and Y. Along the length, now you should pay attention, along the length, flexure stress will vary with the bending moment, M, because bending moment varies along the length of the beam. But through the depth of the beam, the flexure stress will vary and will depend on Y, distance from the neutral axis. Okay? So if either M is zero or Y is zero, flexure stress will be zero. M is zero at the support. So no matter how much Y is, flexure stress will be zero. And Y is zero at the neutral axis. So no matter what the value of M is, F will be zero at the neutral axis. Okay? F will be zero at the neutral axis. And F will be maximum when M is maximum and Y is maximum. And for any other location through the depth of the beam, if Y is known to us, for example, you want to calculate Y at a distance of 2 or 3 inches from the neutral axis, and the M value can be obtained from the bending moment diagram, I is moment of inertia, you can calculate flexure stress. So I hope this is clear to you, that in this manner, we can calculate flexure stress to the depth of the beam if we know the bending moment from the bending moment diagram, and I can be calculated. It is a geometric property of the beam. Y is the distance from the neutral axis. So at any depth from the neutral axis, we can calculate flexure stress in this manner. In a similar manner now, you can also calculate shear stresses to the depth of the beam. V is equal to VQ divided by IB. I and B can be readily calculated from the geometric dimensions of the beam. V can be obtained from the shear force diagram. You know that V is now zero at the midspan. So V is zero at the midspan means the shear stress will also be zero at the midspan. What is Q? Q is basically statical moment. And this statical moment, you look at this, if we want to calculate shear stress at this location C, EC, DC, this, if you want to calculate shear stress at this location. So we will, the shear stress at this location and maximum is the support. So let's say V maximum is the shear force which is obtained from the shear force diagram. IB can be calculated from the dimensions of the beam. How Q can be calculated? Q is basically the area above the line at which the shear stress will be calculated. So above a line, above is this area. Q is the statical moment of the area above the line at which the shear stress will be calculated to the nearest face of the top or bottom of the section. The nearest face, this face, the bottom face is far from CD. The nearest face is the top face. So the nearest face is the top face. This is the area, this area, H area. The statical moment of this H area, which means that area A, B, C, D, and then the centroid of this area, the distance of the centroid of this, from the centroid of this area to the neutral axis, Y bar. So this area A, B, C, D multiplied by Y bar is basically the value of Q. Okay. We can calculate the maximum shear stress very easily if you want to calculate, let's say, shear stress at this location. You can see that the shear stress varies along the through the depth of the beam. If you want to calculate shear stress at this location, we will be obtained from the shear force diagram. IB will be obtained from the dimension of the beam. Q can be obtained now in this manner. Look at the value of Q. From the definition, if you want to calculate the shear stress at this location, so the area above or below this to the nearest face. So area above and below, in this case, they are similar. So let's say we take this area. What is this area equal to? This area is equal to BH by 2. This area is BH by 2. And the statical moment of this from the centroid of this area to the neutral axis will be this distance is h by 4, because if this is h by 2, then half of this will be h by 4. So this will be h by 4. So this will be bh square by 8. Q will be bh square by 8. Now you can simplify this. We can simplify this like this. If Q is equal to bh square by 8 and I bh cube by 12, then shear stress equal to shear stress at the neutral axis, this location. VQ divided by IB, I is bh cube by 12, B is B. So finally you will get a value of shear stress maximum at 3 by 2 V by BH. 3 by 2 is 1.5. What is V by BH? What is V by BH? V is the shear force, and BH is the resisting shear area. Because this is B and this is H. So if you look at a beam which is subjected to this area will basically sheared like this. The area which will be sheared like this. So this is the area which is being sheared. And this area is B times H. So this is the shearing resisting area. And we divide by BH. So this is shear stress. Okay. If we want to draw V by BH on this shear stress diagram, so this value is remain constant and this can be drawn like this. I'm sorry, because 1.5 times this will be, so 1.5 means that this is 50% more than this. If we draw this V by BH on this diagram, it will be like this. V by BH. This is the shear stress. And V maximum is 1.5 times greater than this. If we assume that shear stress varies in this manner to the depth of the beam, then the maximum stress will be 1.5 times this. Now, in the case of reinforced concrete beam, we know that shear stresses cannot be calculated based on these equations. This was just to discuss the case of a homogeneous elastic beam, and so that you understand how shear stresses vary through the depth of the beam, and the basic concepts. The basic concept of shear stress variation through the depth of the beam is recalled, so that you understand the next topics easily. We know that in a reinforced concrete beam, the beam enters into nonlinear inelastic stage well below the ultimate loads in the very beginning. Therefore, this equation of shear stress variation to the depth of the beam, which is usable when the beam is made of homogeneous material and the stresses are in the linear elastic stage, cannot be used for reinforced concrete beam. So, and the problem of shear stress variation to the depth of the beam in reinforced concrete beam is rather complex as compared to flexure stress variation. Okay. For this reason, the data from the tests have been used to obtain a relationship for the shear stress variation to the depth of the beam. Tests have shown that, experimental tests have shown that the average shear stress in a reinforced concrete beam can be expressed by this V divided by BD. H has been replaced by BD. H has been replaced by BD. And this has been done to slightly increase the shear stress, because the shear stress maximum value was 1.5 times V divided by BH. If we replace H by D, so the shear stress will slightly increase. And if we draw this shear stress V divided by BD on the shear stress diagram to the depth of the beam, so this will be the average shear stress to the depth of the beam, and the maximum shear stress value will be slightly more than this. And since in design, the shear stress variation to the depth of the beam, the use of the shear stress variation to the depth of the beam in a design problem in reinforced concrete beam will be of little use, because whatever the shear stresses are in a beam, whether they are at the neutral axis or they are at any other location, when we want to reinforce the beam against the shear stresses, we will provide shear reinforcement in the form of vertical bars, such as stirrups, the area of which will remain constant all along the depth of the beam. It is not possible for us, from practical point of view, to place more reinforcement in the mid depth of the beam than the top and bottom of the beam along the depth of the beam. It is not possible for us. ये मुमकिन नहीं है हमारे लिए कि हम जहाँ पर shear stresses maximum हो, यानी दरमियान में बीम के हम ज़्यादा reinforcement डालें स्ट्रिप्स की शक्ल में और ऊपर और नीचे कम डालें, ये तो मुमकिन नहीं है प्रैक्टिकल पॉइंट ऑफ व्यू से, अनलाइक फ्लेक्सर स्ट्रेसेस। फ्लेक्सर स्ट्रेसेस में क्या होता है कि बीम में टेंसाइल स्ट्रेसेस बॉटम में ज़्यादा होती हैं, तो हम बॉटम में ही reinforcement डालते हैं, ऊपर नहीं डालते, क्योंकि हमें एग्जैक्टली पता होता है कि बॉटम में फ्लेक्सर स्ट्रेसेस सबसे ज़्यादा हैं, तो उधर ही हम reinforcement डालते हैं। लेकिन shear stress वेरिएशन जो बीम के अंदर है, वो दरमियान में shear stress ज़्यादा है और टॉप और बॉटम में कम है। तो अगर उसी एनालॉजी के ऊपर हम reinforcement डालना शुरू करें, तो हम दरमियान में ज़्यादा reinforcement डालेंगे और ऊपर और नीचे कम। मतलब ये है कि स्ट्रिप का एरिया जो है दरमियान में ज़्यादा होना चाहिए और ऊपर, लेकिन ये हम कर नहीं सकते प्रैक्टिकली। हम एक ही स्टेप प्रोवाइड करते हैं, एक ही डायमीटर ऑफ द बार का। तो इस पर्पस के लिए जब इसी चीज़ को देखते हुए हम shear stress को अगर एवरेज shear stress की वैल्यू एज्यूम कर लें कि टॉप से बॉटम तक जो shear stress है वो उसकी जो वेरिएशन है वो V डिवाइड बाई BD के मुताबिक है, और जो मैक्सिमम पार्ट है ये मैक्सिमम पार्ट ऑफ 1.5 टाइम दिस वी विल कवर इनडायरेक्टली, क्योंकि एक्चुअल shear stress जो मिड डेप्थ पे होगा वो थोड़ा सा इस V बाई BD से ज़्यादा होगा, लेकिन उसको हम डिज़ाइन में कवर कर लेंगे, इस वजह से कि अगर हमें shear stress वेरिएशन थ्रू डेप्थ एग्जैक्टली पता भी हो तो फिर भी हमने स्ट्रिप यानी डायमीटर ऑफ द बार या एरिया ऑफ द रिइंफोर्समेंट जो है वो एक ही डालना है ऊपर से नीचे तक, तो उसमें फिर इस चीज़ का फ़ायदा हमें बहुत कम मिलेगा कि हम shear stress को एग्जैक्टली मालूम करें थ्रू डेप्थ ऑफ द बीम। और तो दिस इज द रीजन फॉर द यूजिंग दिस V डिवाइड बाई BD इक्वेशन इंस्टेड ऑफ 1.5 V डिवाइड बाई, एक तो 1.5 V डिवाइड बाई BH की जो इक्वेशन है वो होमोजेनियस इलास्टिक केस में तो बिल्कुल ठीक है, लेकिन रिइंफोर्स कंक्रीट बीम में 1.5 वैल्यू नहीं होगी, 1.3 1.25 के करीब वैल्यू होगी ऑफ दिस। मतलब ये है कि 10 to 20% shear स्ट्रेस इस वैल्यू से ज़्यादा होगा। उसमें थोड़ा सा हम अगर H को D से रिप्लेस करें तो ये और भी कम हो जाएगा, तो तकरीबन 10 to 15% मैक्सिमम shear स्ट्रेस मिड डेप्थ पे इस एवरेज shear स्ट्रेस से ज़्यादा होगा, जिसको हम डिज़ाइन प्रॉब्लम में आराम से कवर कर सकते हैं इस तरह से कि हम स्पेसिंग अगर स्ट्रिप की थोड़ी सी कम कर दें देन द रिक्वायर्ड, सो दिस प्रॉब्लम विल बी रिजॉल्व एंड और ये हम इसलिए कर रहे हैं कि एक तो डिज़ाइन में इस किस्म की परफेक्शंस को अचीव करना बहुत मुश्किल होता है, और फिर इसका फ़ायदा भी नहीं है, जिस तरह मैंने 2-3 दफ़ा कहा कि आप रिइंफोर्समेंट को अलॉन्ग द डेप्थ ऑफ द बीम कम ज़्यादा नहीं कर सकते प्रैक्टिकल पॉइंट ऑफ व्यू से एक ही, तो इसलिए हम ये एवरेज shear stress V डिवाइड बाई BD लेंगे, और टेस्ट से ये चीज़ कंफर्म हो गई है कि ये shear stress की वेरिएशन जो है एवरेज shear stress ये इसके बराबर होती है तकरीबन। Next we will discuss the cracking due to shear stresses. We will discuss the element through the depth of the beam, element 1, 2, and another element 3, which is not shown in this figure, but I will mark this element 3 here. And now I will ask few questions from you. What will be the state of stress in element 3, which I have just marked on the beam? What will be the state of stress in element 3? In this beam, which is simply supported and subjected to uniformly distributed load.
नेग्लिजिबल होगा सर।
क्या चीज नेग्लिजिबल होगा?
3 में सर shear stress है सर।
I'm not talking about the shear stress, I'm talking about the stresses.
Tensile stress.
There will be pure tensile stresses and there will be no shear stresses, not negligible, no shear stresses. This is a case of pure tensile stresses like this. No shear stresses here. Okay? And when there are two opposing forces like this in the form of tensile forces, which will produce tensile stresses, what will be the direction of the crack produced by these tensile stresses? The direction of the crack.
So downwards या upward जाएगा.
The direction will be vertical crack. Because if these are two pulling forces, then they will pull apart this element and a crack will appear like this. Correct? And if you remember, you have seen in several videos which we watched in the beginning that due to flexural stresses, a crack appears in the bottom of the beam, which makes an angle of 90 degrees with the horizontal, and the crack slowly and gradually moves upward, okay, depending on the value of the load, a bending moment. So a flexure crack will appear like this vertically, and this you have seen in the videos, flexure crack. Okay, what will be the state of stress in element 1?
Pure shear stress, sir.
Shear.
Paver shear stresses. Element 1 is subjected to paver shear stresses. Okay? And if you remember, you have used Mohr circle to calculate principal tensile and compressive stresses from a stress state to which an element is subjected to. So if this element 1 is subjected to paver shear stresses, what will be the value of principal tensile and compressive stresses on a Mohr circle?
It will be 0, sir.
जी
सर 0 होगा सर टेंसाइल स्ट्रेसेस.
आपका क्या नाम है?
वसीम सर.
वसीम, आप कह रहे हैं कि जीरो, क्या जीरो होंगे? इधर जो नॉर्मल स्ट्रेसेस है ना, दैट विल बी जीरो, बट आई एम टॉकिंग अबाउट द प्रिंसिपल स्ट्रेसेस. प्रिंसिपल स्ट्रेसेस, you are right that the stresses, because this element is at the mid depth, so there will be no tensile stresses and no compressive stresses on element 1, which are normal stresses. Okay, but I am talking about the principal stresses. If you transform the case of paver shear stresses on a Mohr circle, you will find that the principal stresses, principal tensile and compressive stresses will be equal to the shear stresses, but they will be oriented at an angle of 45 degrees. If you calculate the angle of the principal tensile stresses, the angle will be 45 degrees between the principal stresses, and then the angle with the horizontal. The angle with the horizontal of the principal stresses will be 45 degrees, and the principal tensile stresses, both tensile and compressive stresses, will be equal to the shear stresses. And this case is just equal to this thing. The case of paver shear stresses can be represented by this state of stress using Mohr circle. The element is, if the element, this case is just like this case. The element is oriented at an angle of 45 degrees, and you have principal compressive stresses and principal tensile stresses. And this we can prove very easily. Now you look at the element 1, which is shown in figure B. Okay, look at the element 1. The top left corner of element 1 will be moved to the left and up, upward and to the left. Upward and to the left means it will be somewhere here. Correct? Because the shear stresses will move this corner of the element 1 to the left, and this shear stress will move this upward. So upward and to the left. So this corner will be moved here. Similarly, the bottom right corner of element 1 will be moved to the right and downward. So it will come somewhere here. Similarly, the top right corner will be moved down and to the left, and the bottom left will be moved upward and to the right. Now, if we redraw this element 1, the deformed shape of element 1 will be like this after the shear stress act on this. And you can see that there is elongation of length along this diagonal. And whenever there is elongation of length, you know that there are some tensile stresses acting on the element. Because without the tensile stresses, elongation is not possible. And there is shortening along this, so this means that there is a compression. So this case is just equal to this case. You can see now the two cases, they are exactly equal. So either with the help of Mohr circle or with the help of the deformed shape of the element 1, you can prove that the case of paver shear stresses is just like the principal stresses acting at an angle of 45 degrees with the horizontal. There are tensile stresses acting along the diagonal and compressive stresses acting along the diagonal. And you know that concrete is weak in tension. So whenever there is elongation along this diagonal, the tensile stresses are acting in this direction. So the crack will appear perpendicular to the direction of these stresses in this manner. So which means that if I mark this crack here in element 1, the crack will appear like this. Okay, the angle is roughly speaking 45 degree. I hope this is clear. So for element 3, the crack will be vertical. For element 1, it will be approximately at an angle of 45 degree with the horizontal. And on element 3, this angle is 90 degree. What will be the state of stress for element 2? Element 2 is subjected to tensile stresses, but not the maximum tensile stresses, because the maximum tensile stresses will occur in element 3. And similarly, there will be no maximum shear stress in element 2, because maximum shear stresses occur in element 1. There will be tensile stresses and shear stresses in element 2 acting simultaneously, and then the crack will appear, which will not be at an angle of 90 degree and not at an angle of 45 degree, somewhere between 90 and 45, maybe at an angle of 60 or 70, and slightly and gradually it will become 45 like this. So the crack, due to flexure and shear stress, both will be like this. Correct? Okay?
Yes, sir.
Okay, what will be the crack orientation at the midspan of the beam? At the midspan of the beam, the orientation of the crack at the midspan of the beam. Because at the midspan of the beam, shear stress is 0 if the beam is subjected to uniformly distributed load. So the crack cannot turn horizontal, it will be like this, because there are no shear stresses. Even at the mid depth, shear stress is 0 because V is 0, shear force is 0. And very close to the support, the bending moment value is 0, very close to support. So crack cannot appear like this. Crack will appear like this at the mid depth. And similarly on this, it will be like this. These cracks, which appear at the mid depth and roughly at an angle of 45 degree, are called pavor shear crack, are called web shear crack. Pavor shear crack or web shear cracks. The web shear cracks. And these cracks are called flexure cracks because they are pavor flexure. And these cracks, which are the result of flexure and shear, both they are called flexure shear cracks. So there are 3 types of cracks. Flexure cracks, which are at an angle of 90 degree with the horizontal, and they will appear from the bottom of the beam and will move upward. Then you have pavor shear cracks, which will appear at the mid depth and at an angle of 45 degree approximately. And you have flexure shear cracks, which appear both due to both flexure and shear actions. This has been shown in this slide number 10. You can see a beam which has been subjected to, so you can see vertical cracks here, and you have at the supports, near the supports, there is a shear crack. Similarly, here flexure shear cracks are also here. Okay. So web shear cracks are those cracks which are formed at location where flexure stresses are negligibly small. Flexure cracks we have discussed previously, but there are 2 types of shear cracks, and shear cracks are generally called as diagonal tension cracks. Diagonal tension cracks, and the reason is that these cracks are oriented at an angle of 45 degree, roughly speaking. So they are, and because they will produce tensile stresses at one of the diagonal of the element like this, along this element. So because, and the crack will appear on this diagonal perpendicular to direction of tensile stresses. So they are called as diagonal crack, because this crack is appearing along one of the diagonal of the element. This crack is appearing along one of the diagonal of the element. Okay, excuse me. So these cracks appear along the diagonal of the element. They are called diagonal tension crack because the pivot shear stresses will further reduce tensile stresses, principal tensile stresses at an angle of 45 degree with the horizontal. And these tensile stresses will basically cause cracking of the concrete along one of the diagonals. So for this reason, the shear cracks are called as diagonal tension cracks. Okay, they are also called shear cracks, but they are also called diagonal tension cracks. And then there are two types of diagonal tension cracks. One are web shear cracks, which appear at mid depth like this, and they will appear at locations where flexure stress is 0 and shear stresses are very large. And flexure shear cracks will appear at locations where shear forces and bending moments both have large values. And this can happen at the interior supports. You know that interior support there will be negative bending moment and as well as maximum shear. So the crack will appear due to flexure from top to bottom, not from bottom to top, because these are positive bending moment areas. In the case of positive bending moment areas, the crack will appear from bottom to top because tensile stress will occur here. And in the case of bending moments at the supports, you know that bending moment is maximum at the support, so it will produce tensile stresses in the top part of the beam. For this reason, cracks will appear in the top part of the beam, and then the crack will propagate downward. Okay, and flexure cracks and flexure shear cracks both will be produced near the supports. Next, I will show you a video wherein you will be able to see what happens if a beam is not designed for shear. Okay, watch this video, please. you can see the crack due to shear is much larger and dangerous. It split the beam into two pieces than the flexure stresses. If you recall the video that you have watched in the beginning when we were discussing flexure stresses, the cracks were minor as compared to these cracks. This crack is very wide and split the beam into two pieces. So this is very dangerous. Okay, two important things that we learn from this video are, number one, that the shear stress failure, that the failure due to shear stresses is more dangerous than the flexure failure. Shear failure of reinforced concrete beam is more dangerous than the flexure failure, because the flexure failure was a ductile failure, but the shear stress failure due to shear stresses is brittle in nature. And this is very sudden failure. So it is a sudden, brittle, and dangerous failure. Sudden, brittle failure, and because of this sudden failure and brittle failure, it is dangerous. The flexure failure was very gradual, and it was ductile, so it is not as dangerous as shear failure. Okay, this is one thing that keeping in view the mode of failure, we can see, and we have seen, that failure of a reinforced concrete beam due to shear stresses is more dangerous than flexure stresses, number one. And number two is that we have seen that although we did not provide any kind of shear reinforcement, the beam was still capable of resisting shear stresses up to a large extent. And the reason is that concrete alone is also very good in resisting shear stresses, unlike flexure stresses case. In the case of flexure tensile stresses, in concrete is not capable of resisting tensile stresses, and if you remember, we neglect the contribution of resisting tensile stresses from concrete, and the whole contribution comes from reinforcement, steel reinforcement. However, in the case of shear stresses, as you will see, that the contribution from concrete will not be ignored, and it will be used in our calculations. I will show you another video which is also similar to this video, wherein you will be able to see again the shear failure, which is sudden in nature, sudden and brittle in nature.
Starting to apply vertical loads to the specimen, and the beam starts to deflect. Then quite suddenly, we have an explosive failure near a support. This is what we call a shear failure, and it is something that we always want to avoid. If we slow down the footage, here is that failure again. Look how sudden it is. Now remember, this is a beam in which we have left out the shear reinforcement, and this is the consequence.
So in both these cases, shear reinforcement has not been provided. With these videos, you can realize the importance of shear reinforcement in beams. Okay, next we will see the nominal shear capacity of a reinforced concrete beam. The nominal shear capacity of reinforced beam is partly comes from concrete and partly comes from reinforcement if it is provided. Okay. In the case of flexure, the nominal bending moment capacity or nominal flexure capacity was taken by reinforcement only, and this contribution from concrete was taken as 0. So Mn was equal to Ms, and Ms was equal to As Fyd minus A by 2. In the case of shear, as we have seen in the previous 2 videos, that even till failure, there is resistance from concrete in shear, and that shear capacity, that is called shear capacity of concrete, it will be utilized in the case of shear design. Okay. So it will be Vc plus Vs, and Vc will not be taken equal to 0. Vc will be used in our equations. Vc comes from where? First of all, the value of Vc basically is contributed from Vcz plus Vd and plus Vi. If you look at this beam where the crack has appeared, so if we join the other part of the beam on the right side, you will see that when these 2 sides are joined like this, there is a compression force at the top portion of the beam, and when you compress 2 blocks of concrete against one another, it will become difficult for it will become difficult to slide these 2 blocks. The sliding of the blocks will become difficult due to what? Due to the application of compressive forces, because the compressive forces will prevent the sliding, because the compressive forces will increase the friction between the 2 blocks, and it will become difficult to slide these 2 blocks against one another. So partly this compressive force, which is produced due to the bending of the beam, these are called flexural compressive stresses. So the flexural compressive stresses will keep the top portion of the beam intact, or it will enable the top portion of the beam, the top fibers of the beam, to resist shear stresses due to these flexural compressive stresses. So this will come from Vcz. Vcz is the compression resistance in this. This is the compressive force, and the resistance will come. The resistance Vcz will come in this manner. In the shear, this will come from friction. When these 2 blocks are compressed against one another, so Vcz, this is the resistance in shear. If these 2 blocks are slide against one another, so the resistance will be the resistance due to friction, which is produced by these compressive forces, will resist this shear stress V, and this will be equal to Vcz. Vc, because this is compression, and Z is the vertical direction of this. You know that whenever a block is kept on a surface, okay, and if it is compressed, so this the sliding resistance will increase. If you want to move this with the force V, the sliding resistance will increase with this when this force N, which is the compressive force, increases, and this sliding force will be equal to mu times N, where mu is the coefficient of friction between the 2 surfaces, and N is the compressive force. We do not want to enter into this mu N kind of derivation, but Vcz will appear, and Vcz will help the concrete elements in resisting shear stresses. So one is this contribution. The second contribution comes from this steel reinforcing bar. The steel reinforcing bar, which has been placed primarily for tensile stresses, will also help the 2 parts of the beam to remain together. And when the 2 parts of the beam are separated by the application of shear forces, this force If this force is applied there and this part of the beam on the right is to be separated or slided downward from this part, so there is a horizontal reinforcement in this across these two parts. So this horizontal reinforcement, which stretches across these two portions, will also resist the separation of these two parts of the beam. This is called double action. This is called double action because the reinforcement is placed across these two parts, so it will become difficult to separate these two bars due to the placement of this reinforcement which exists across the crack. This action is called as double action. So the other is double action due to the flexure reinforcement, and VIY is another action which is basically the interlocking action. Because initially the cracks which will appear will be very small, and slowly and gradually the crack will increase. But in the beginning, when the crack appears, the interlocking action between the two parts of the concrete interlocking due to friction, this interlocking action will also resist the shear stresses. So finally, this VC, VD, and VI will produce a shear resistance which has been experimentally calculated and is equal to 2FC prime BWD. Okay, 2 times FC prime square root of FC prime BWD. Now I'll ask you to calculate the shear capacity of a beam only due to concrete with the help of this equation, for FC prime equal to 3000 psi and B equal to 12 inch and D equal to 18 inch. Please quickly calculate this. In order to convert the value of shear capacity into kip, please divide this value, whatever is obtained from the equation, by 1000.
$23.66.
33.66, yes, you are right. So this is the capacity, this is the shear capacity of concrete. You should remember, and you should also be very careful about the terminology. Okay, the terms that we are using should be very careful, and you should carefully listen to the terminology. This is called the shear capacity of concrete. Shear capacity of concrete. If no reinforcement is provided in a beam, this capacity will be given by concrete alone, which means that if shear demand is less than this, theoretically speaking, no shear reinforcement is required. Okay, there are equations also given on the right side in a table. These equations are not to be used in this lecture, but if you look at this equation, the first equation especially, this one, there is another term with this 2 lambda FC prime. This is NU divided by 6 AG. NU means N is the compressive force. If there is an axial compressive load applied on a beam or on a column, then the shear capacity will increase by this amount, NU divided by 6 AG. Since in the case of beams, normally this NU is 0, so this term will become 0, and you will be left with 2 lambda FC prime BWD, and lambda for normal concrete is 1, so you will get this equation, 2 FC prime BWD. The other equation we will not discuss at this moment. If you want to discuss and if you want to learn, you can go to the relevant sections of the ACI code 22.5.5.1. We will be using this equation 2 FC prime BWD, which is good enough for shear design of reinforced concrete beam. Okay, this was contribution from concrete. Now contribution from reinforcement. If we place stirrups across the crack like this, these are stirrups placed across the cracks. So when you want to slide this part on the right against the part on the left, so stresses will be produced in these vertical stirrups equal to AV into FY, because the resistance will be offered by steel bar. AV, And mind that there are two legs of these stirrups on one side and the other side. So this AB will be multiplied by 2 always. If this is number 3 bar, the area of number 3 bar is 0.11, but since these are two legged reinforced bars, so this will be 2 multiplied by 0.11, 0.22, and Fy is the yield strength of steel. Okay, this will be the resistance offered. So Vs, which is the resistance of steel, will be equal to AVFy, but it will depend on the number of stirrups across the cracks. Let's say there are n number of stirrups placed across the cracks. So then it will be NAVFY, 1, 2, 3. It can be more or less. So let's say the number of stirrups across the cracks are n. So the resistance offered by the stirrups will be equal to NAVFY. Okay, and if the distance, this distance of the crack, the horizontal distance of this crack is, let's say, P. So N can be calculated if spacing is S between the stirrup. You know that then N will be equal to P divided by S, because P is the length, horizontal length of the portion of the beam which is cracked, and the number of cracks are N. The spacing between the stirrup is S, so the total number of cracks will be equal to P divided by S. And roughly speaking, this P, if this angle of the crack is 45 degrees, this P will be approximately equal to the effective depth of the beam. So this P can be replaced by D. This will be D divided by S AVFY. So you will get this equation like this. Vs, which is the resistance from the stirrup, will be equal to Vs is equal to AVFY D divided by S. And as I said earlier, and I say again, AV will be 2 times the area of steel used for this reinforcement, because it will be 2 legs of this reinforcement. Now, the total design shear capacity, and Vn is nominal shear capacity. Vn is equal to VCS, Vc plus S. These are nominal capacities. The design capacity, when Vn is multiplied by 5, so that to reduce this for factor of safety, it will become 5Vn is equal to 5Vc plus 5Vs. We know that to avoid shear failure, 5Vn must be greater than or equal to Vu. At least 5Vn shall be equal to Vu. So then this 5Vc plus 5Vs should be equal to Vu, because this is 5Vn. And we have just recently calculated 5Vs. So 5Vc will be equal to 5AVFYD divided by S equal to Vu. And from this spacing of the stirrups we want to calculate, S will be equal to this equation. 5AVFYD, 5AVFYD divided by Vu minus 5Vc. 5Vc you can calculate from the previous equation. Phi is taken as equal to 0.75 for shear, because shear is more dangerous than flexure. In the case of flexure, phi was taken equal to 0.9. So there was a 10% reduction from the nominal, and there is a 25% reduction from the nominal. For 2 reasons. One is that the shear behavior through the depth of the beam is not exactly known to us, and the other is that shear failure is dangerous. Then the flexure failure. So spacing of the stirrups. Now the spacing can be calculated by assuming AV. Normally we use number 3 bar for stirrups, which is 3 by 8, and the area is 0.11. So this will be 0.11 multiplied by 2, 0.22. Phi is 0.75. Fy, let's say 40 or 60, D is the effective depth, which will be known to us. Vu will come from the shear force diagram, and 5Vc will come from the equation phi 2Fc prime BWD. So we can calculate the spacing of the stirrups required. Vu, what value of Vu shall be taken? Generally speaking, Vu is maximum at the support. As you know this, when a beam is subjected to uniformly distributed load, but it is not the maximum shear at the support which need to be taken in the calculation. Because if you look at these 2 parts of the beam, if these 2 parts of beam are joined together, then you will see that this part of the beam on the right is being slided against this part on the left. So it is this load which is on the right side of this, on the right part of the beam, is sliding the left part on the, because the load on the left part of the beam is directly going to the support, without causing any shear crack or shear stresses. So it is the load on the right of this beam which is causing these shear stresses. So there is no need of taking maximum shear which is at support. We can take shear stress which will come from this load at a distance of d from the face of the support. ACI code allows you that if there is a shear force diagram like this, so there is no need to take maximum shear, but take the, for the design purpose, take the shear force value at a distance of d from the face of the support. आप देखें इसमें मैं अगर आपको फिर बता दूं, for those of you who want to understand this, ये हम क्यों करते हैं. असल में ACI कोड में दो किस्म की प्रोविजंस गिवन है डिजाइन पर्पस के लिए. एक तो वो प्रोविजन है जो सिर्फ सेफ्टी को एड्रेस करती है, उसमें आप किसी किस्म की चेंज नहीं कर सकते, लेकिन वो एक प्रोविजन है इकोनॉमी के लिए. तो ये भी एक इकोनॉमी का प्रोविजन है. अगर आप इधर मैक्सिमम शेयर ले लें, यानी ये शेयर आप ले लें, तो आपके पास स्टेप ज़्यादा आ जाएंगे, क्योंकि जब शेयर ज़्यादा फोर्स होगा तो रिफोर्समेंट भी ज़्यादा आ जाएगी. लेकिन अगर आप ACI कोड आपको अलाउ करता है कि आप एट डिस्टेंस ऑफ डी शेयर ले लें, तो ये शेयर जो आप ले लेंगे तो थोड़े स्टेप आपको कम आ जाएंगे. और ACI कोड ने इसका रीज़न ये दिया है क्योंकि ये जो आपका राइट का पार्ट है, असल में इस पर जो लोड है ये शेयरिंग काज करता है अगेंस्ट दिस लेफ्ट पार्ट, और लेफ्ट पे जो लोड है वो तो शेयरिंग नहीं कर रहा, वो डायरेक्टली सपोर्ट को लोड ट्रांसफर कर रहा है. तो लिहाजा ये लोड जो है इसको लेना फिर ज़रूरी नहीं है. और राइट वाला जो लोड है, तो इससे इसका फ़ायदा ये है कि थोड़ा सा हमारा काम जो डिज़ाइन का है वो इकोनॉमिकल हो जाएगा, और अगर आप मैक्सिमम शेयर भी ले लें तो थोड़े 2-3 स्टेप ज़्यादा आ जाएंगे. तो दिस प्रोविज़न इज़ फॉर द पर्पज़ ऑफ इकोनॉमी. हम डिज़ाइन में आमतौर पे मैक्सिमम शेयर लेते हैं क्योंकि उसमें डिस्टेंस ऑफ डी हम नहीं लेते, लेकिन फॉर द एकेडमिक पर्पस के लिए ये चीज़ आपको समझना भी चाहिए, और आप अपने एग्जाम्पल में भी फिलहाल इसको इस तरह किया करें. अच्छा, देन देयर आर सम केसेस गिवन बाय द ACI कोड. ये तो टिपिकल केसेस हैं ए बी, जिसमें एक बीम है यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड है, तो उसमें आप क्रिटिकल शेयर डिस्टेंस ऑफ डी ले लें. ये कंटिन्यूस बीम है दूसरे का, उसमें भी आप, तो ये ए बी में ये तो टिपिकल सपोर्ट कंडीशन है. कुछ कंडीशन ऐसी हैं जिसमें आप डिस्टेंस ऑफ डी नहीं लेंगे बल्कि मैक्सिमम शेयर लेंगे. एक सूरत ये है कि इसी डी के अंदर आपका एक हेवी पॉइंट लोड लगा हो, यानी इधर कोई रेत की बोरियां हैं या सीमेंट की बोरियां हैं जो बिल्कुल कॉलम के करीब लगी हुई है, दीवार के करीब, तो फिर आप मैक्सिमम शेयर लेंगे, डिस्टेंस ऑफ डी नहीं लेंगे. एक इन्वर्टेड बीम है, यानी उसमें स्लैब नीचे है और बीम ऊपर है, तो उस केस में भी आप मैक्सिमम शेयर इधर लेंगे. इस किस्म का हैंगिंग बीम है कि बीम हैंग्ड है किसी इस तरह मेंबर से, तो उसमें भी आप इस तरह लेंगे. यू विल बी नॉर्मली यूजिंग दिस ए एंड बी, हम डिस्टेंस ऑफ डी लेंगे. अच्छा जी, अब आप देखें एक बहुत अहम 20 and 21 स्लाइड्स, 3-4 स्लाइड ये बहुत अहम है, इसको जरा गौर से आप देखें. ACI कोड की प्रोविजंस ये हैं. देखिए, शेयर फोर्स डायग्राम, इन दिस फिगर यू कैन सी हाफ ऑफ द शेयर फोर्स डायग्राम इज बीन ड्रॉन. यू नो, आपको पता है कि फुल शेयर फोर्स डायग्राम एक इसका ऐसे होगा. ये हाफ शेयर फोर्स डायग्राम अगर हम इस वक्त देख लें तो ये हमने हाफ शेयर फोर्स डायग्राम ड्रा किया. इस पे जो ये वी जो आपको नजर आ रहा है, ये वो शेयर है जो डिस्टेंस ऑफ डी है, यानी मैक्सिमम शेयर नहीं है, उसको हमने निकाल दिया इसमें से. अच्छा, अगर इस शेयर फोर्स डायग्राम के ऊपर मैं कैपेसिटीज को प्लॉट कर दूं तो मैं 5EC तो मालूम कर सकता हूं फॉर एनी बीम. 5EC इज 0.75 2 FC प्राइम स्क्वायर रूट BWD. लेट्स से कि ये VU की जो वैल्यू है ये है 100, ये है लेट्स से 50 के. ठीक है जी, और इधर वैल्यू है 0. ये शेयर फोर्स डायग्राम है. अब मैं शेयर फोर्स डायग्राम के ऊपर ही कैपेसिटीज को प्लॉट करता हूं, क्योंकि यूनिट्स तो सेम है, इसका यूनिट भी कैप है और इसका भी कैप है, और दोनों ये शेयर कैपेसिटी और वो शेयर फोर्स है. तो ये 0.75 × 2. अभी आप लोगों ने मालूम किया था, अगर BW हमारे पास 12 इंच हो और D हमारे पास 18 इंच हो, तो 5EC कितना आ जाएगा? FC प्राइम 3000 है।
ट्वेंटी फोर
0.75 से आपने मल्टीप्लाई कर लिया,
सेवनटीन पॉइंट सेवन फोर
17.7
हाँ 17.74, ठीक। लेट्स से 18, बस 18 आ गई। तो ये वैल्यू 18 किप हो गई और ये वैल्यू 5EC/2 ये 9 किप हो गई। अच्छा, अब ये तो शेयर फोर्स डायग्राम है ना, ये शेयर फोर्स डायग्राम है, तो इधर शेयर फोर्स की वैल्यू 5EC/2 से भी कम है, ठीक है कि नहीं? ये तो शेयर फोर्स डायग्राम है, इसकी हर वैल्यू शेयर फोर्स की वैल्यू है। मैंने इसमें कैपेसिटीज को प्लॉट किया ताकि मुझे पता चल जाए कि कहाँ कहाँ पर शेयर फोर्स मेरी इस कैपेसिटी से कम है और कहाँ पर ज्यादा है। तो इधर जो शेयर फोर्सेज हैं इधर तक, ये तो हाफ ऑफ द शेयर कैपेसिटी से भी कम है, ठीक है ना? और इधर जो वैल्यूज हैं वो हाफ ऑफ द शेयर कैपेसिटी से ज्यादा है, लेकिन फुल 5EC से कम है। और इस रेंज में जो वैल्यू हैं वो शेयर कैपेसिटी से, डिजाइन शेयर कैपेसिटी से वो वैल्यू ज्यादा हैं। तो इसमें 3 पोर्शन बन रहे हैं। एक वो पोर्शन कि जिसमें शेयर फोर्सेस हाफ ऑफ द शेयर कैपेसिटी से भी कम है, ये वाला पोर्शन। और दूसरा पोर्शन जिसमें वैल्यू 5EC से तो कम है लेकिन 5EC/2 से ज्यादा है। और तीसरा वो जिसमें, तो वी विल बी लुकिंग एट दिस 3 पार्ट्स ऑफ द शेयर फोर्स डायग्राम। ACI कोड हमें क्या कहता है? As you have seen that shear force, the shear failure is much more dangerous than the flexure failure for this reason. ACI कोड वैसे theoretically तो ये होना चाहिए था कि अगर 5EC से VU कम हो तो हमें शेयर रिइंफोर्समेंट की कोई ज़रूरत नहीं होनी चाहिए थी। लेकिन ACI कोड वो कहता है कि नहीं, इस तरह आप न करें। ACI कोड कहता है कि आप 5EC को 2 पर डिवाइड करें और अगर शेयर कैपेसिटी को 2 पर डिवाइड करने के बाद भी ये शेयर डिमांड से ज्यादा वैल्यू आ रही है कैपेसिटी की, यानी हाफ ऑफ द कैपेसिटी को आप 2 पे डिवाइड करें फिर भी वो शेयर डिमांड से ज्यादा है VU से, तो उन लोकेशन में आपको कोई शेयर रिइंफोर्समेंट प्रोवाइड करने की जरूरत नहीं है। लेकिन अगर सिर्फ 5EC VU से ज्यादा है मगर 5EC/2 VU से कम है तो उस लोकेशन में फिर आप शेयर रिइंफोर्समेंट प्रोवाइड करेंगे। कहने का मतलब ये है कि इस जगह पर तो आपको इजाजत है कि आप शेयर रिइंफोर्समेंट डालें, लेकिन इस जगह पर थ्योरेटिकली तो हमें कोई रिइंफोर्समेंट डालने की जरूरत नहीं होनी चाहिए थी। लेकिन ACI कोड कहता है कि नहीं, इस जगह पर भी आप शेयर रिइंफोर्समेंट प्रोवाइड करेंगे और उसके लिए ACI कोड ने 4 इक्वेशन दिए हैं और इस 4 इक्वेशन में जो कम वैल्यू आपको मिले उसके मुताबिक आप कोड कहता है कि आप AVFY डिवाइड बाय 50 BW, ये वैल्यू जरा आप मालूम करें, आप आराम से मालूम कर सकते हैं। अगर BW हमारे पास 12 इंच हो, अगर BW हमारे पास 12 इंच हो और AV हमारे पास 0.22 हो, FY हमारे पास 60,000 हो, तो आप इस इक्वेशन से मालूम करें। और D हमारे पास लेट से 18 इंच है, 24 इंच, और इससे भी मालूम करें। 4 इक्वेशन से ज़रा मालूम करके मुझे बताएं और इसमें लीस्ट वैल्यू कौन सी आ रही है ये भी बताएं।
सर फर्स्ट इक्वेशन से 22 आ रहा है।
हाँ, सबसे मालूम करें और मुझे बताएं फिर।
सर FC प्राइम आपने नहीं बताया कितना है?
3000 ले, 3000।
सर ये D/2 से 9 आता है, ये ठीक है सर?
हाँ ठीक है, बिल्कुल सही।
सर D/2 वाला मिनिमम।
सर D/2 मिनिमम है।
इससे क्या आ रहा है?
26.77।
26.77।
तो D/2 आमतौर पे आपको ये वैल्यू जो है ये कम मिलेगी। अच्छा, ये चारों इक्वेशन से ये उस वक्त आप प्रोवाइड करेंगे कि आप का जो डिमांड है VU शेयर फोर्स वो 5EC से तो कम है लेकिन 5EC/2 से ज्यादा है, तो उस सूरत में ये होगा। ठीक है, लेकिन अगर 5EC/2 VU से ज्यादा है तो फिर आपको शेयर के लिए कोई इन्फोर्समेंट डालने की जरूरत नहीं, लेकिन फिर भी हम प्रोवाइड करते हैं। कोड कहता है कि आप ना प्रोवाइड करें, लेकिन मैं आपको कहता हूं कि फिर भी हम 12 इंच पे प्रोवाइड करते हैं। अब हमारे पास अगर वो कंडीशन है कि जिसमें 5EC VU से कम है, तो फिर तो आपके पास इक्वेशन है, ये वाला इक्वेशन है। इस इक्वेशन को अगर आप देखें जरा गौर से, जो भी हमने डिराइव की थी इक्वेशन, इसमें 5EC कैपेसिटी है और VU डिमांड है। अगर 5EC VU से ज्यादा है तो दिस वैल्यू विल बिकम नेगेटिव। ठीक है कि नहीं?
यस सर।
अगर 5EC VU के बराबर तो 0, तो एस इनफाइनाइट हो जाएगा। इसका मतलब ये है
Yes.
कि जब तक 5EC VU से ज्यादा है या VU के बराबर है, तो इस इक्वेशन से आप S की कोई स्पेसिंग मालूम कर ही नहीं सकते हैं। जी आप उस वक्त कर सकते हैं जब 5EC VU से कम हो। समझ रहे हैं?
Yes, sir.
यस सर।
जब 5EC VU से कम है तो आप इससे स्पेसिंग मालूम करेंगे। अगर 5EC VU से ज्यादा है, 5EC VU से ज्यादा है, तो फिर इस इक्वेशन से आप तो कोई वैल्यू मालूम नहीं कर सकते हैं। लेकिन अगर 5EC/2 VU से ज्यादा नहीं है, ठीक है, तो उस केस में आप क्या करेंगे, ये चार इक्वेशन जो भी हमने इस्तेमाल की, इसमें से मिनिमम वैल्यू आप ले लेंगे, इसमें लीस्ट वैल्यू ले लेंगे, उसको उन लोकेशन पे आप इस वैल्यू को इस्तेमाल करेंगे। अच्छा, फिर इसमें एक और बात भी गौर से सुने। अगर आपके 3 लोकेशन है जिस तरह के हमने अभी डिस्कस किए, देयर आर 3 डिफरेंट डिस्टिंक्ट लोकेशंस along the length of the beam. One was the area in which 5EC/2 was greater than V shear force. तो उसमें तो आपको इख्तियार है कि आप डालें या न डालें, लेकिन मैं आपको कहता हूं कि आप 12 इंच पे कम से कम डालें। दूसरा वो पार्ट ऑफ द बीम है जिसमें 5EC/2 और 5EC के दरमियान शेयर फोर्स है, उसके लिए आप ये 4 इक्वेशन इस्तेमाल करेंगे और इसमें जो लीस्ट वैल्यू हो तो उसके मुताबिक आप स्ट्रिप की स्पेसिंग रखेंगे। अब आखिरी एरिया रह गया, आखिरी में आप इस इक्वेशन से मालूम करेंगे, लेकिन अगर ये स्पेसिंग इस स्पेसिंग से ज्यादा आ गई तो फिर आप ये स्पेसिंग प्रोवाइड करेंगे, इस मैक्स वाली स्पेसिंग, मैक्सिमम स्पेसिंग। ठीक है, क्योंकि वो तो जो बिल्कुल आखिरी पार्ट है, बिल्कुल सपोर्ट के करीब, उसमें तो स्पेसिंग आपको बिल्कुल करीब करीब रखनी चाहिए। लेकिन अगर ये डिजाइन स्पेसिंग यानी 5EC और VU में फर्क बहुत कम है तो आपकी स्पेसिंग बहुत ज्यादा आ जाएगी। ठीक है ना? जब ये स्पेसिंग ज्यादा आ जाए तो फिर आप वो स्पेसिंग न प्रोवाइड करें, बल्कि इसमें जो स्पेसिंग आपके पास आ जाए कम से कम उस स्पेसिंग को आप उस लोकेशन में भी प्रोवाइड करें। अब मैं जरा एक दफा फिर कहता हूं कि आप इस डायग्राम को देखें। इस लोकेशन में इन द जो बिल्कुल सेंटर ऑफ द बीम के करीब है, इसमें आपको स्ट्रिप की थ्योरेटिकली जरूरत नहीं है, लेकिन आप 12 इंच पे प्रोवाइड करें। इस लोकेशन में आप 4 इक्वेशन से जो आपके पास कम स्पेसिंग आ जाए, जिस तरह 9 इंच आ गए तो 9 इंच करें। इस लोकेशन में अगर आपकी स्पेसिंग इस इक्वेशन से इससे कम आ गई तो आप वो स्पेसिंग प्रोवाइड करें। मिनट से ये 9 इंच है, 7 इंच है तो आप 7 करें। लेकिन अगर इधर 12 इंच स्पेसिंग आ गई, उधर 9 इंच है, तो फिर आप इधर भी 9 इंच करेंगे आखिरी पार्ट में भी। दिस विल बी आल्सो 9 इंच। समझ गए इस बात को?
Yes, sir.
Now there are 2 more equations. One equation is for ये तो इसकी बहुत कम इस्तेमाल होती है, लेकिन फिर भी आप इसको देखें। 5ES असल में क्या है? 5ES जो है ना, 5EC प्लस 5ES इज इक्वल टू VU। तो 5EC किसके बराबर है जी? VU माइनस 5EC। अगर VU और 5EC का फर्क बहुत ज्यादा हो तो 5ES की वैल्यू बहुत ज्यादा हो जाएगी, यानी आपको बहुत ज्यादा स्टेप्स डालने पड़ेंगे और बहुत क्लोजली प्लेस करने पड़ेंगे। 5ES की वैल्यू अगर इस वैल्यू से बढ़ जाए 5.8 FC प्राइम BWD, जो कि शेयर कैपेसिटी के 4 गुना है, क्योंकि शेयर कैपेसिटी 5 2 FC प्राइम BWD है 5EC। तो अगर ये 5ES इतना यानी VU और 5VU और शेयर डिमांड बहुत ज्यादा है और 5EC बहुत कम है, तो इस केस में 5ES बहुत ज्यादा हो जाएगा। अगर 5ES इतना ज्यादा हो गया कि वो 58 FC प्राइम BWD से भी बढ़ गया, तो फिर आप बीम की कैपेसिटी को सिर्फ 5ES से इंक्रीज न करें, बल्कि डेप्थ बढ़ाएं ताकि थोड़ा 5EC भी आपका बढ़ जाए, क्योंकि सिर्फ 5ES इस सूरत में काम नहीं करेगा। इसका मतलब ये कि डेप्थ आपने बहुत कम ली हुई है, तो इतनी कम डेप्थ ये अलाउड नहीं है एज पर ACI कोड। दूसरा ये है कि अगर 5ES ये जो VU माइनस 5EC है 8 टाइम्स FC प्राइम BWD से ज्यादा नहीं है, लेकिन 4 टाइम्स FC प्राइम BWD है, ठीक है ना। इसका मतलब ये है कि ये चीज अगर आप देखें तो असल में ये चीज किया है, ये 2 टाइम्स 5EC है। 5EC इज 5 2 FC प्राइम BWD, तो ये 5 2 5EC है। तो अगर 5ES VU और 5EC का फर्क इतना ज्यादा है कि ये 2 टाइम्स है 5ES, तो आप इसको फिर क्या करेंगे, जो मैक्सिमम स्पेसिंग की 3 इक्वेशंस है ना, उसको आप ऐसे एडजस्ट करेंगे कि उनसे जो भी वैल्यू आपके पास फाइनली आ जाए मिनिमम वैल्यू, उसको फर्दर 2 पे डिवाइड करें। जिस तरह कि आपने अभी मालूम कर ली वैल्यू 9 इंच आ रही थी, तो इंस्टेड ऑफ 9 इंच you divide again this by 2 and you will use spacing equal to 4.5 inch. Although very rarely these two equations will be used, लेकिन इसको आप चेक जरूर करें। ये तो हमने डिस्कस कर लिया ऑलरेडी। नेक्स्ट इज एन एग्जांपल, वी कैन क्विकली गो थ्रू दिस एग्जांपल। इतना आसान है ये एग्जांपल, मुश्किल नहीं है। इसमें एक बीम है 20 फीट लॉन्ग एंड यू हैव अ डेड लोड 0.75 के पर पोर्ट 0.75 के पर। जी प्लीज
सर, ये ब्रेक के बाद
क्लास ना। जी जी प्लीज यू कैन आस्क योर क्वेश्चन।
सर मैं कह रहा था सर ब्रेक के बाद नहीं कर सकते?
ब्रेक के बाद आई हैव अ मीटिंग नाउ एट 12:30, तो मैं मीटिंग में जाऊंगा, फिर मुमकिन ना होगा। तो इसलिए मैं चाहता हूं कि ये एग्जांपल है, इसको मैं ज़रा आपके साथ जल्दी कर लूं, फिर नेक्स्ट टाइम अगर आपको क्वेश्चन हो आप क्वेश्चन कर सकते हैं। इसमें मुश्किल नहीं है, बहुत आसान है, आप ज़रा इसको देखते रहें। इसमें डेड लोड और लाइव लोड गिवन है, ACI कोड 318-19 के मुताबिक डिज़ाइन करना, FC प्राइम FY एवरीथिंग इज गिवन टू यू। These steps are already covered in the flexure design. H minimum is equal to L by 16, B and D. These things we have already covered in flexure design. इसको मैं नहीं करूँगा। This H is 18 inch, effective depth is DH minus Y bar. Y bar is taken as 2.5 inch, so D is equal to 15.5 inch. This is the same example which we discussed in the flexure design. This is the ultimate load, 1.2 times WD plus 1.6 times live load. Self weight of the beam is calculated. So the ultimate load is 2.37 kip per foot UDL on a simply supported beam. Then you can draw the shear force diagram and bending moment diagram. This beam we have already designed for flexure, so we are not going to discuss this. We will only discuss the shear part. Okay, this is the shear part. This is the critical shear, which is calculated at distance of D. You can calculate this VU. This is Vmax. Vmax. We will not use Vmax in our design. We will use VU, which is at a distance of D. By a similarity of these two triangles, you can calculate this very easily. We know that the shear force will be 0 at the at the center of the beam, mid span. So let's say the beam is 20 feet. This beam is 20 feet long. This will be 10 feet. So 23.7 divided by 10 is one triangle, y divided by x, and the other is the VU divided by 10 minus D. This distance is D. And the effective depth is 15.5, which means it is 1.29 feet. So it is 1.29 feet. From this similarity of triangle, you can calculate VU. VU is the critical shear, which is 20.64 kip. Then you will calculate, okay, the flexure, I will skip this part because this flexure design, you already done this. The shear part. In the shear part, PU is 20.64 kip, 5EC is 5.2 FC prime BWD 0.75, this is 15.28 kip, 5EC is 15.28, this is less than 24 kip, so we have to design this. Now assuming number 3 two-leg vertical slip, design spacing, phi AVF by dVu minus phi VC can be very quickly calculated, 0.75, 0.22, and 40, 15.5, 20.64, minus 15.8. This gives us a spacing of 19.1 inch. And as I said earlier, now we will calculate maximum spacing using these four equations. This is AVFY divided by 50 BW. This gives you a value of 14.6 inch. D by 2 is 7.75 inch, 24 inch, and the other value is 17. So the minimum value is 7.75 inch. This 7.75 inch spacing is even less than the design spacing which we have calculated in the previous step. It is 19.1 inch. So 5VS check is also clear. 5V4 check is also clear. Finally, this is the placement of stirrup reinforcement. In this location, theoretically, no reinforcement is required. In this location, the maximum spacing 7.75 inch shall be used. In this location, although the spacing is 19.12 inch, but as I said earlier, quite a few times, that S maximum 7.75 inch. If this is less than the design spacing, you will use also design spacing in this location. So 7.75 inch spacing will be used in this location as well. The placement of stirrup shall be done in this manner. The ACI code says that the first stirrup shall be placed at a distance of spacing divided by 2. The spacing in this case is 7.75 inch divided by 2, which means 3.8 inch. The first stirrup will be placed at a distance of 3.8 inch from the face of the support, not at a distance of D. You should note down this. Although in the calculation of spacing, we use VU critical shear, which is calculated at distance of D, but the placement of stirrups will be done at a distance of S by 2 from the face of the support. S by 2 in this case, S is 7.75 inch, so S by 2 is 3.8 inch. So first strip will be placed here. Then the strips will be placed up to this location, where shear is 5EC by 2. Using the strips will be placed at the rate of 7.75 in central center. And from this point up to the other side of the beam, from the zero shear, this spacing will be 12 inch, and the remaining part will also be in this location, 12 inch, in this location, and on this location, on both left and right, we will place spacing of stirrup. We'll provide stirrup at a spacing of 7.75 in center to center. So this is all in this lecture. This is the final detailing. You go through, please, this detailing of the drafting. And if you have any question, you can come up with questions. These are a few class activities. I will ask my teacher to upload this lecture today so that you can go through these class activities and you can solve these problems yourself. If you have any question, please come up with questions in the next lecture. Now we have a meeting. So please accept my apologies for ending the lecture before the time of the end time of this lecture. If you have any question, you can come up with questions next time. Thank you. Allah Hafiz.
Ele kada attendance chat wargawe.
Patengin na kita surog na no.
Bala bacho mula punyat minat Allahu Akbarum.
Ila ka recording na ko do.
Oh shit.